95% of the universe is something we cannot see. Not because it is far away, not because our instruments are too weak, not because it hides behind something brighter. It is invisible because it does not interact with light at all. It does not emit it. It does not reflect it. It does not absorb it. And yet it built the universe. Everything you have ever seen, every star, every planet, every mountain, every ocean, every atom in your own body accounts for roughly 5% of what exists. The other 95% is made of something else entirely, something that has shaped galaxies, guided the formation of stars, and determined the large-scale structure of the cosmos, all without ever being seen. Welcome to Sleep Knowledge. If you find comfort in exploring how much of reality remains quietly present but invisible to us, settle in and let tonight's exploration unfold slowly. And if you feel moved to share where you are drifting off tonight, it is always warming to know how far these gentle thoughts travel. Tonight, we will move through three of the most fascinating and least understood components of the universe: dark matter, dark energy, and black holes. Not to make the cosmos feel overwhelming or unknowable, but to understand what scientists have discovered, what observations have revealed, and why these invisible forces are not a mystery to fear, but a wonder to sit with quietly. And perhaps, by the end, to see that the universe is not less trustworthy for containing things we cannot yet fully explain. It is simply larger than we once imagined. The universe looks full when you look up at the night sky. Stars scatter across the darkness in familiar patterns. The moon glows with borrowed light. Planets trace slow arcs across the heavens. Everything seems accounted for. Light fills space. Matter fills light. The story feels complete. For most of human history, this impression went unchallenged. What you could see was what existed. What glowed was what mattered. The universe was made of the stuff that announced itself through brightness. That impression turns out to be deeply incomplete. Not wrong in the way that early maps were wrong about the shape of continents. Incomplete in a quieter, more fundamental way. Like looking at a vast landscape at dusk, seeing the trees and the hills and the river, but not yet realizing that beneath the soil, an entire network of roots and water and living systems stretches far beyond what the surface suggests. The universe is like that. The visible part is real. The stars genuinely burn. The planets genuinely orbit. But beneath that visible layer, something much larger provides the structure, the scaffolding, the gravitational agreement that holds everything in place. And that something does not shine. To understand why, it helps to begin with something familiar. It helps to begin with light itself. Light is how we know the universe exists. Almost everything astronomy has ever learned came through the detection of light in some form. Visible light, radio waves, infrared, ultraviolet, X-rays, gamma rays, all of these are forms of electromagnetic radiation, and all of them are how objects in space announce their presence. A star does not need to be visited to be known. It simply needs to emit or reflect light, and a telescope, pointed correctly, can read that signal across billions of light years. This dependence on light made astronomy powerful, but also, in a subtle way, limited. Because if something does not emit light, does not reflect light, and does not absorb light, then no telescope, no matter how sensitive, will ever detect it directly. It will remain invisible to every instrument ever built for the purpose of looking. For a long time, this limitation did not seem like a problem. There was no reason to suspect that anything important existed beyond the reach of light. The universe appeared to be made entirely of the kind of matter that shines, or at least the kind that could shine if conditions were right. That assumption began to crack in the early 20th century. Quietly, not with a dramatic announcement, but with a slow accumulation of observations that did not quite fit. The first hints came from watching galaxies. A galaxy is a gravitational system, an immense collection of stars, gas, dust, and other material, all moving together, all bound by a shared gravitational field. Stars within a galaxy orbit a common center, much the way planets orbit a star. The motions are slow by human standards, but precise by astronomical ones. And because the motions are governed by gravity, they follow predictable patterns. If you know how much mass a galaxy contains, you can calculate how fast its stars should orbit. The math is straightforward. More mass means stronger gravity. Stronger gravity means faster orbits. This relationship had been understood for centuries, built from the same gravitational principles that explain how planets circle the Sun. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a group of galaxies called the Coma Cluster. He measured how fast those galaxies were moving within the cluster, then estimated the total mass of visible matter, all the stars and gas that could be detected through light. He then calculated how fast the galaxies should have been moving, given that amount of mass. The numbers did not agree. The galaxies were moving far too fast. According to the visible mass alone, they should not have been held together at all. They should have been flying apart, escaping the cluster's gravitational pull. But they were not flying apart. They were staying put, orbiting steadily, bound together by something. Zwicky proposed that there must be additional mass that did not emit light, mass that could not be seen. He called it dunkel materia, dark matter. At first, the idea was met with skepticism, a reasonable response. Claiming that something invisible and undetectable exists requires extraordinary evidence, and in the 1930s, the evidence was suggestive but not yet conclusive. It took decades of further observation before the case for dark matter became difficult to argue against. The clearest early evidence came not from clusters, but from individual galaxies, and specifically from how they rotate. Picture a spiral galaxy seen from above, like a slow-turning pinwheel. Stars near the center orbit quickly, pulled inward by the dense concentration of mass at the core. Stars farther out orbit more slowly, because they are farther from that central mass and feel weaker gravitational pull. This is the same pattern seen in our own solar system. Mercury races around the Sun. Saturn drifts. Neptune crawls. The outer planets move slower because they are farther from the gravitational center. Galaxies should behave the same way. Outer stars should orbit more slowly than inner ones. This pattern is called a Keplerian decline, named after the astronomer Johannes Kepler, who first described how orbital speed decreases with distance. In the 1970s, an American astronomer named Vera Rubin began systematically measuring the rotation speeds of stars across entire galaxies. She and her colleague Kent Ford used spectrographs instruments that split light into its component wavelengths to detect tiny shifts in the color of starlight caused by the star's motion. These shifts, known as Doppler shifts, revealed how fast each star was moving and in which direction. What Rubin found was unexpected. The outer stars of galaxies were not slowing down. They were moving at roughly the same speed as the inner stars. The rotation curves, when plotted on a graph, came out nearly flat where they should have been declining. A gentle curve downward that never came. This was not a measurement error. Rubin and Ford checked their work carefully, and other astronomers repeated the observations across dozens of galaxies. The flat rotation curves appeared again and again, in galaxy after galaxy, regardless of size or type. The implication was clear, though it took time to fully absorb. If outer stars were orbiting just as fast as inner ones, then there must be more mass in the outer regions of galaxies than the visible stars could account for. Significantly more. Something invisible was providing the gravitational pull needed to keep those outer stars in orbit. Dark matter was no longer a speculation. It was becoming an observational fact. So far, we have seen that galaxies rotate faster than their visible matter should allow. But rotation curves are only one way the universe reveals its hidden mass. There is another method, and it is perhaps even more striking. It comes not from watching how things move, but from watching how light bends. Light travels in straight lines. That is what everyday experience suggests, and for most purposes, it is true. A beam of light crossing an empty room goes from one side to the other without curving. It does not detour. It does not meander. But space is not always empty, and where mass is present, space itself curves. This is one of the central insights of Einstein's general relativity. Massive objects do not simply pull on other objects through invisible threads. They reshape the geometry of space around them. And light, traveling through that reshaped space, follows the new geometry. Its path bends. This effect is called gravitational lensing. The word lensing is apt. A glass lens bends light by changing the medium it travels through. Gravity bends light by changing the shape of the space it travels through. The result is similar. Images are warped, magnified, or multiplied. Astronomers discovered gravitational lensing in the early 20th century, shortly after Einstein's general relativity was confirmed. But it took decades before the effect became a practical tool. What made it useful was a realization. If you can measure how much light is bending around a massive object, you can calculate how much mass must be present to produce that bending. And critically, that calculation does not care whether the mass is visible or not. This means gravitational lensing can detect dark matter directly, not by seeing it, but by measuring its gravitational fingerprint on the light that passes near it. NASA's Hubble Space Telescope has produced stunning images of gravitational lensing in action. Distant galaxies, far beyond a massive cluster, appear stretched into arcs and rings, their light warped by the enormous gravitational field of the cluster in front of them. When astronomers calculate the mass needed to produce those distortions, they find far more mass than the visible galaxies and gas in the cluster could provide. The difference is dark matter, enormous, invisible, and unmistakably present. One of the most compelling pieces of evidence for dark matter came in 2006 from a collision between two galaxy clusters known as the Bullet Cluster. Galaxy clusters are already immense structures. Hundreds or thousands of galaxies, bound together by gravity, drifting through space as a single gravitational unit. When two clusters collide, what happens is extraordinary. Not the galaxies themselves crashing into each other. The spaces between galaxies are so vast that direct collisions are rare. What collides is the hot gas between the galaxies. Gas heated to tens of millions of degrees, filling the space between stars like a thin, scorching atmosphere. When the Bullet Cluster collision was studied by astronomers using NASA's Chandra X-ray Observatory, something remarkable emerged. The hot gas, which is the dominant visible component of a galaxy cluster, slowed down during the collision. It piled up, compressed, and heated further, creating a bright X-ray signature that marked exactly where the gas had come to rest. But the galaxies themselves, moving through the gas like ships through water, passed through each other with relatively little resistance and continued on their way. Here is where dark matter became undeniable. When astronomers mapped the total mass of the system using gravitational lensing, the mass did not follow the gas. It followed the galaxies. The invisible mass, the dark matter, had sailed through the collision alongside the galaxies, unaffected by the gas, unimpeded by the collision. It behaved exactly as a form of matter that does not interact with anything except gravity would behave. The Bullet Cluster did not prove that dark matter exists in a single decisive moment. Science rarely works that way. But it made the case so clean, so visually clear, that alternative explanations became extremely difficult to sustain. Dark matter had passed the test that skeptics had set for it. Now that we have seen how dark matter reveals itself through rotation curves, through gravitational lensing, through the bullet cluster, a natural question arises. What is it, actually? What is dark matter made of? The honest answer, as of today, is that no one knows for certain. Dark matter has been detected through its effects on everything around it, but the substance itself has never been directly observed or identified. It remains one of the deepest open questions in physics. But scientists have not simply shrugged and moved on. Decades of theoretical work and experimental effort have produced a set of leading candidates, hypothetical particles that could, if they exist, account for dark matter's behavior. The most widely discussed candidate is a class of particles called WIMPs, weakly interacting massive particles. The name is precise. WIMPs, if they exist, would be massive, heavier than any particle currently known, and they would interact with ordinary matter only through the weak nuclear force, one of the four fundamental forces of nature and gravity. They would not interact with light at all. They would pass through ordinary matter like ghosts, leaving almost no trace. This is exactly why dark matter is dark. If it is made of WIMPs, it cannot shine, because it does not couple to electromagnetic radiation. It cannot be seen, touched, or felt in any ordinary sense. Only gravity betrays its presence. Experiments around the world have been searching for WIMPs for decades. Deep underground laboratories, shielded from cosmic radiation by kilometers of rock, house extraordinarily sensitive detectors designed to catch the rare moment when a WIMP might collide with an atomic nucleus. The LZ experiment, located deep beneath the Black Hills of South Dakota, is among the most sensitive detectors ever built. As of recent observations, it has not yet detected a WIMP, but the search continues and the detectors grow more sensitive with each generation. Another candidate is the axion. Axions are hypothetical particles that were originally proposed in the 1970s to solve a different problem in particle physics, but theorists quickly realized they could also serve as dark matter. Unlike WIMPs, axions would be extraordinarily light, far lighter than an electron. And like WIMPs, they would interact with ordinary matter only very weakly. Axion searches use a different approach. Rather than waiting for a particle to collide with a detector, they use powerful magnetic fields to try to convert axions into photons, particles of light, which could then be detected. Experiments like ADMX, the Axion Dark Matter Experiment at the University of Washington, have been refining this technique for years. There are other candidates as well. Sterile neutrinos, primordial black holes, and other exotic possibilities have all been explored. Each comes with its own set of predictions and its own set of challenges. None has yet been confirmed. What this means is that dark matter sits at a fascinating intersection. Its effects are well established. Its presence is not in serious doubt. But its nature remains genuinely unknown. It is one of those rare cases where science can say with confidence that something is there, while remaining honestly uncertain about what that something is. That uncertainty is not a failure. It is where the deepest exploration happens. Dark matter does not simply exist alongside the visible universe. It shaped it. To understand what this means, it helps to think about how the universe came to look the way it does. Billions of years ago, shortly after the universe began, matter was spread almost uniformly across space. Almost. There were tiny variations in density regions that were, by the faintest margin, slightly denser than others. These variations were extraordinarily small. The difference between a denser region and a less dense one was comparable to the difference between two drops of water, one containing a single extra molecule. But gravity is patient. Over hundreds of millions of years, those tiny density differences began to grow. Matter in the slightly denser regions pulled on matter nearby, drawing it inward. The denser regions became denser still. The less dense regions lost matter to their neighbors and thinned out. This process, known as gravitational collapse, is how the first structures in the universe formed. Stars, galaxies, clusters. The cosmic web of filaments and voids that fills the observable universe today. All of it grew from those faint initial whispers of density. And dark matter was essential to that process. Here is why. In the very early universe, ordinary matter, the stuff made of protons, neutrons, and electrons, was tightly coupled to light. Photons and ordinary particles were in constant contact, exchanging energy, bouncing off each other in a dense fog. This meant that ordinary matter could not collapse freely into dense structures. Whenever it tried to clump together, the pressure of light pushed it back out, smoothing the clumps away before they could grow. Dark matter, however, does not interact with light. It does not feel that outward pressure. It is free to collapse under its own gravity without resistance. And so, in the early universe, dark matter began forming structures long before ordinary matter could. It assembled itself into halos, vast invisible gravitational wells, and those halos then attracted ordinary matter into them once the fog of light cleared. The galaxies we see today sit inside dark matter halos. The stars and gas and dust that make up the visible parts of galaxies are, in a sense, guests in structures that dark matter built first. This has been confirmed by observations from NASA's Planck satellite, which mapped the faint afterglow of the early universe, a relic of light left over from when the cosmos was only about 380,000 years old. The patterns in that ancient light, tiny fluctuations in temperature, match precisely what would be expected if dark matter had been driving structure formation from the very beginning. Without dark matter in the models, the patterns do not form correctly. With it, they align beautifully with what telescopes observe today. Dark matter is not a passenger in the story of the universe. It is one of the architects. There is something quietly humbling in this realization. The visible universe, everything that has ever been photographed, studied, measured, and known, is a thin layer of decoration on a much deeper structure. The galaxies glow, the stars burn, but the framework that holds them in place, the gravitational scaffolding that determined where they would form and how they would move, is made of something that has never been seen. And yet the universe is not less stable for it. It is more so. Dark matter provides the gravitational glue that keeps galaxies together, that holds clusters intact, that preserves the structure of the cosmos across billions of years. Without it, galaxies would fly apart. Stars would drift into the void. The ordered universe we observe would dissolve into chaos. The invisible holds the visible in place. That is not a troubling thought. It is a reassuring one. Now, dark matter accounts for roughly 27% of the universe's total energy content. Ordinary matter accounts for about 5%. Together, they make up roughly 32% of everything. That leaves 68% unaccounted for. This is where the story takes its strangest turn, because that remaining 68% is not matter at all. It is not made of particles. It is not a substance in any conventional sense. It is something else entirely. Something that behaves not like matter, but like a property of space itself. Scientists call it dark energy. And understanding dark energy requires understanding something about how the universe is expanding. In 1929, an American astronomer named Edwin Hubble made an observation that changed cosmology forever. By carefully measuring the light from distant galaxies, he discovered that those galaxies were moving away from us. and not just moving away the farther a galaxy was, the faster it was receding. This pattern, now known as Hubble's law, suggested something extraordinary. The universe was expanding. Not galaxies flying through a fixed background of space, but space itself stretching, carrying the galaxies along with it like raisins in a rising loaf of bread. No matter which direction you looked, galaxies were moving away. And no matter which galaxy you stood on, every other galaxy would appear to be receding. There was no center, no edge, just expansion, uniform and gentle, happening everywhere at once. This discovery was confirmed and refined over the following decades. The cosmic microwave background radiation, the faint afterglow of the early universe, provided independent confirmation. The abundance of light elements like hydrogen and helium matched predictions based on an expanding, cooling universe. By the mid-20th century, the expanding universe was one of the best supported ideas in all of science. But expansion alone does not require dark energy. Expansion simply means that the universe got larger over time. It says nothing about whether that expansion is speeding up, slowing down, or proceeding at a constant rate. And that is where the surprise came. In 1998, two independent teams of astronomers set out to answer a seemingly straightforward question. Is the expansion of the universe slowing down? Intuition suggested it should be. After all, gravity is attractive. If the universe expanded outward from some initial event, then gravity should be pulling everything back together, gradually decelerating that expansion. The universe was expanding, yes, but it should have been slowing down as it did so. Both teams used a particular type of star as their measuring tool. These are called Type Ia supernovae stars that explode in a remarkably consistent way, always reaching roughly the same peak brightness. Because their brightness is predictable, they can be used as what astronomers call standard candles. If you know how bright something actually is, and you can measure how bright it appears from Earth, you can calculate exactly how far away it is. The two teams measured dozens of Type Ia supernovae at enormous distances across the universe. They expected to find that the more distant ones were slightly brighter than predicted, a sign that the universe had been expanding more slowly in the past, and that gravity had been doing its job of slowing things down. What they found was the opposite. The distant supernovae were fainter than expected. Fainter meant farther away than predicted. And farther away than predicted meant that the universe had been expanding more slowly in the distant past, and was now expanding faster. The expansion was accelerating. Gravity was not winning. Something else was. Something was pushing the universe apart, and it was getting stronger over time. The discovery earned the team's leaders Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. It was one of the most surprising findings in the history of cosmology, and it required an explanation. That explanation is dark energy. Dark energy is not a substance in the way matter is a substance. It does not come in particles. It does not have mass in the conventional sense. It is better understood as an intrinsic property of space itself, a kind of energy that is built into the fabric of the universe, present everywhere, and that exerts an outward pressure. As the universe expands, more space comes into existence. And because dark energy is a property of space, more dark energy comes with it. This means that as the universe grows, the outward push of dark energy grows with it, while the gravitational pull trying to slow expansion remains tied to the fixed amount of matter that already exists. Over time, dark energy wins more and more decisively. The expansion accelerates. The idea that space itself could contain energy is not as strange as it initially sounds. Einstein himself included a term in his equations of general relativity called the cosmological constant, which represented exactly this possibility, an energy density inherent to empty space. He introduced it in 1917 to produce a static universe, which was the dominant model at the time. When Hubble discovered that the universe was actually expanding, Einstein reportedly called the cosmological constant his greatest blunder. But it turned out not to be a blunder at all. It turned out to be a prediction. The cosmological constant, reinterpreted as dark energy, is now one of the most important concepts in modern cosmology. What dark energy actually is, at a deeper level, remains one of the greatest open questions in physics. Is it truly a constant the same everywhere, at all times? Or does it vary, changing subtly as the universe evolves? Current observations suggest it has been remarkably stable, but the measurements are not yet precise enough to rule out slow changes. The James Webb Space Telescope, launched in 2021, and upcoming missions like the Euclid spacecraft and the Vera Rubin Observatory are designed in part to study dark energy with unprecedented precision. They will measure the expansion rate of the universe at different points in its history, looking for any sign that dark energy is not what it appears to be. For now, dark energy remains as mysterious as dark matter, but its effects are undeniable. It is reshaping the future of the universe. It is the reason the cosmos is expanding faster today than it was a billion years ago, and it accounts for the largest share of everything that exists. So we have dark matter invisible, gravitationally active, responsible for the structure of galaxies and clusters. And we have dark energy, a property of space itself, driving the accelerating expansion of the universe. Together, they account for 95% of the total energy content of the cosmos. And now, the story turns towards something that connects them both. Something that is in many ways the most dramatic expression of gravity in the universe. A place where space-time itself is stretched to its limits, where nothing that enters can ever return, and where the boundary between the known and the unknown becomes almost impossibly thin. Black holes. Black holes feel like they belong to science fiction. Objects so massive that nothing can escape them. Regions of space where gravity becomes so intense that even light is pulled inward and swallowed. The idea carries a certain dramatic weight, and popular culture has amplified that weight considerably. But the reality of black holes is quieter, and in many ways more fascinating than the drama suggests. They are not monsters lurking in the dark. They are a natural consequence of how matter behaves when compressed beyond a certain point. They are products of the same gravitational laws that keep the Earth in orbit around the Sun. And they are, in a sense, the universe's way of showing what happens when gravity is given enough mass and enough time. To understand black holes, it helps to understand how they form. Stars are a kind of balance. On one side is gravity, pulling inward with immense force, trying to compress the star into the smallest possible space. On the other side is the pressure generated by nuclear fusion, the process by which hydrogen atoms are fused into helium in the star's core, releasing enormous amounts of energy. That energy pushes outward, resisting the inward pull of gravity. As long as the balance holds, the star shines steadily. The Sun has been maintaining this balance for about 4.5 billion years. It will continue for, roughly, another 5 billion. The hydrogen fuel in its core is vast, and the process is slow and steady. But stars do not last forever. Eventually, the fuel runs out. The nuclear reactions that have sustained the star for billions of years begin to fail. The outward pressure weakens. Gravity, which has been waiting patiently, begins to win. What happens next depends on the mass of the star. For stars like the Sun, or smaller, the collapse is gentle. The star contracts into a dense but stable remnant called a white dwarf, supported by a quantum mechanical effect called electron degeneracy pressure. It will glow faintly for trillions of years, slowly cooling, gradually fading into darkness. A quiet end for a star that burned steadily for billions. For stars significantly more massive than the Sun, 8 times more massive or greater, the ending is more dramatic. When the fuel runs out, the core collapses rapidly and violently. The outer layers of the star crash inward, then rebound in an explosion so energetic that the star briefly outshines an entire galaxy. This is a supernova. What remains after the explosion depends, again, on mass. If the remnant is massive enough, but not too massive, it collapses into a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Neutron stars are supported by neutron degeneracy pressure, another quantum mechanical effect that resists further compression. But if the remnant is massive enough, generally 3 or more times the mass of the Sun, even neutron degeneracy pressure cannot hold. Nothing can. The core collapses further, past any known point of equilibrium, into something from which there is no return. A black hole. The boundary of a black hole is not a surface in the way a planet has a surface. There is no solid ground, no atmosphere, nothing to touch or land on. The boundary is a region in space called the event horizon. It is defined not by any physical barrier, but by a condition, the point at which the escape velocity equals the speed of light. Escape velocity is the speed an object must reach to break free of a gravitational pull. On Earth, escape velocity is about 11 kilometers per second. A rocket moving faster than that will leave Earth's gravity behind. On a more massive planet, escape velocity is higher. At the event horizon of a black hole, escape velocity reaches the speed of light, the fastest anything in the universe can travel. And since nothing can move faster than light, nothing that crosses the event horizon can ever escape. Not light, not matter, not information of any kind. This is why black holes are black. Light that enters does not come back out. No signal can escape to tell us what happens inside. The event horizon is a one-way door. From the outside, a black hole does not look like a void or an emptiness. It has gravitational effects that are detectable, measurable, and real. It bends light. It warps space-time around it. It can pull material inward, heating it as it falls, creating glowing disks of gas that can be extraordinarily bright. These accretion disks are some of the most energetic phenomena in the universe, and they are powered by the same gravity that makes the black hole invisible at its core. What happens inside the event horizon is one of the deepest mysteries in physics. General relativity predicts that at the center of a black hole lies a singularity, a point where density becomes infinite and space-time curvature becomes infinite. But physicists are cautious about this prediction. Infinity, in physics, usually signals that a theory has reached the edge of its validity. It suggests that something deeper is happening that the current equations cannot yet describe. The singularity may not be a real feature of nature. It may be a place where general relativity quietly admits it needs help. This is where black holes connect to the deeper questions about dark matter and dark energy. All three phenomena point toward the limits of current understanding. All three tell us that the universe contains more than our theories have yet fully accounted for. And all three do so not through chaos or disorder, but through consistent, measurable, gravitationally coherent behavior. The most famous black hole in our own galaxy sits at the center of the Milky Way. It is called Sagittarius A*, pronounced Sagittarius A star. For decades, astronomers suspected that a supermassive black hole lurked at the galactic center. The evidence came from the motion of stars near the center of the Milky Way. These stars orbit something extremely massive, contained within a region too small to be a cluster of smaller objects. Astronomers tracked these stars over years and decades, watching their paths curve and bend as they swung around the invisible center. The star called S2 has been observed for over 20 years. It follows an elongated orbit, swinging close to the galactic center every 16 years before arcing out again. At its closest approach, it moves at nearly 3% of the speed of light. The mass required to produce that orbit, concentrated within a region so small, could only be one thing. In April 2019, the Event Horizon Telescope produced an image that made this conclusion visible for the first time. The Event Horizon Telescope is not a single telescope, but a network of radio telescopes spread across the globe, linked together to function as one vast instrument. Its first published image was not of Sagittarius A*, but of the supermassive black hole at the center of a galaxy called M87, located 55 million light-years away. That image showed a dark central shadow surrounded by a glowing ring of heated gas. The accretion disk, lit up by the energy of material falling inward. The shadow itself was the event horizon, silhouetted against the glow. In May 2022, the Event Horizon Telescope released an image of Sagittarius A times itself. The image was blurrier because Sagittarius A times is smaller and closer, and the gas around it moves faster and more chaotically. But the structure was unmistakable. A dark center, a ring of light, the gravitational shadow of a black hole 4 million times the mass of the Sun, sitting quietly at the heart of our own galaxy. It has been there for billions of years. It did not arrive recently. It did not threaten anyone. It simply sits at the center, shaping the orbits of stars, influencing the slow rotation of the galaxy, existing as a massive but peaceful gravitational anchor. This is an important point. Black holes, despite their fearsome reputation, are not predatory. They do not reach out and pull things in from vast distances. Their gravity is strong only very close to them. At the distances that separate stars within a galaxy, a black hole's gravity is no different from that of any other object of the same mass. If the Sun were somehow replaced by a black hole of equal mass, the planets would continue orbiting in exactly the same paths they orbit now. Nothing would fall in. The solar system would simply go dark. Black holes are dramatic in concept, but gentle in practice. They are the universe's quietest extremes. And yet there is one more thing about black holes that challenges even the most carefully constructed theories. It is a prediction made by the physicist Stephen Hawking in 1974, and it fundamentally changed how physicists think about what black holes are. Classical physics, following general relativity, suggests that black holes are permanent. Once formed, they exist forever, growing larger as they consume more matter. Nothing escapes. Nothing diminishes them. They are, in a sense, the most enduring objects in the universe. Hawking showed that this is not quite right. His reasoning drew on quantum mechanics, the physics of the very small, and applied it to the edge of a black hole. In quantum mechanics, empty space is not truly empty. It is constantly producing pairs of particles, a particle and its antiparticle, which spring into existence together and almost immediately annihilate each other, returning to nothingness. These are called virtual particle pairs, and they flicker in and out of existence everywhere, at all times, as a fundamental feature of the quantum vacuum. Near the event horizon of a black hole, something unusual can happen to these pairs. If one particle of the pair drifts across the event horizon before the two can annihilate, it falls into the black hole and cannot return. The other particle, left behind on the outside, becomes real. It escapes into space as genuine radiation. This is Hawking radiation. The energy for that escaping particle must come from somewhere, and it comes from the black hole itself. Each particle that escapes carries away a tiny amount of the black hole's mass energy. Over an extraordinarily long time, far longer than the current age of the universe for any black hole we know of, this slow loss would eventually cause the black hole to evaporate completely. Hawking radiation has not been directly observed. The effect is extraordinarily faint for any black hole of significant mass. A stellar mass black hole would take longer than the current age of the universe to evaporate noticeably. A supermassive black hole like Sagittarius A times would take incomprehensibly longer still. The prediction is taken seriously by physicists because the reasoning behind it is sound and because it has profound implications. It means that black holes are not eternal. Given enough time, they will fade. They will return their mass to the universe, particle by particle, across spans of time so vast that they make the current age of the cosmos seem like the opening moments of a story. There is something quietly reassuring in this. Even the most extreme objects in the universe participate in larger cycles. Even the darkest, most inescapable regions of space-time are not permanent fixtures. They are temporary, in the deepest sense of that word. And the universe continues, patient and unhurried, long after they have gone. Black holes also revealed something about the fabric of space-time itself, through a phenomenon that Einstein predicted, but that took over a century to detect. When two black holes orbit each other and eventually spiral inward and merge, the collision sends ripples outward through space-time. These ripples are called gravitational waves. They are not waves in space, they are waves of space itself, stretching and compressing the fabric of the universe as they pass. Einstein predicted gravitational waves in 1916 as a consequence of general relativity. For decades, they remained theoretical. The effect was predicted to be extraordinarily small, smaller than any instrument of the time could detect. On the 14th of September 2015, the LIGO detectors made history. LIGO, the Laser Interferometer Gravitational Wave Observatory, is a network of extraordinarily sensitive instruments with arms stretching 4 kilometers in length, designed to measure changes in distance smaller than a single proton. On that morning, both the detector in Hanford, Washington, and the one in Livingston, Louisiana, registered the same signal simultaneously. The signal was the gravitational wave produced by two black holes, each roughly 30 times the mass of the Sun, spiraling toward each other and merging into a single, more massive black hole. The merger released more energy in a fraction of a second than all the stars in the observable universe combined. And it did so silently, invisibly, detectable only through the faintest possible ripple in the geometry of space. Since that first detection, LIGO and its partner detector Virgo have observed dozens of gravitational wave events. Each one confirms general relativity with remarkable precision. Each one reveals something about the black holes involved, their masses, their spins, their histories. Gravitational waves have opened an entirely new way of listening to the universe. Not seeing it, not photographing it, listening to it. Detecting the vibrations that space-time itself produces when the most massive objects in the cosmos collide. There is a moment in any deep exploration of the cosmos where individual objects begin to blur into patterns, where galaxies stop being things and start being points in a structure, where clusters become intersections rather than endpoints, and where the universe reveals itself not as a collection of separate pieces, but as a single, continuous, living arrangement. That arrangement has a name. It is called the cosmic web. The cosmic web is the largest structure in the observable universe. It is not an object in the way a galaxy or a star is an object. It is more like a landscape, a vast three-dimensional network of filaments, walls, and voids that fills the space between galaxies and clusters. Filaments are long, thread-like regions where matter is concentrated, running across millions of light-years of space. Walls are broader sheets of matter, extended surfaces in 3 dimensions. And voids are the enormous empty regions between them, regions where almost nothing resides, stretching across hundreds of millions of light-years. Seen together, these components give the universe a texture. Something like a honeycomb, or a piece of foam, or a net stretched across infinite space. Dense strands surround enormous empty bubbles, Matter traces the edges and intersections, leaving the centers largely clear. This structure is not random. It is not the result of chance. It is the grown-up version of those tiny density differences that existed in the earliest moments of the universe. The cosmic web is the amplified echo of the initial conditions, those faintest whispers of variation that dark matter, over billions of years, turned into the vast architecture we observe today. Computer simulations based on known physical laws produce patterns that match what telescopes observe almost exactly. Feed the simulations the right initial conditions, the density variations measured by the Planck satellite, and let them run for 13 billion years. The result looks remarkably like the universe. Filaments where filaments are observed. Voids where voids are observed. Clusters at the intersections where clusters are found. Dark matter is the primary ingredient in this web. It forms the invisible scaffold along which visible matter flows. Galaxies drift along filaments, guided by gravity toward cluster intersections. Gas streams through the web, feeding star formation over billions of years. And the whole structure continues to evolve, slowly, as the universe expands and dark energy stretches the distances between its parts. The cosmic web is one of those structures that rewrites how you think about the universe. Not as a collection of things scattered through empty space, but as a single continuous pattern, shaped by simple physical laws acting across immense spans of time. Matter did not fall randomly into galaxies. It followed paths laid out by dark matter halos, flowing along channels that had been carved by gravity since the universe was young. The voids in the web are not just absences. They are essential parts of the pattern. Matter flowed away from them early in cosmic history, drawn toward denser regions by gravity. Over time, the contrast sharpened. Dense regions grew denser. Empty regions grew emptier. Some of the largest features in the universe are defined not by what is present, but by what is absent. A void can span hundreds of millions of light years and contain only a handful of galaxies. It is enormous, not because it is heavy, but because it is empty. Space itself becomes a structural element. There is something gently calming in the idea of the cosmic web. It suggests that the universe is not chaotic, not disordered, not a random scattering of matter into the dark. It is organized. It has a pattern. That pattern emerged naturally from simple initial conditions through simple physical laws over a long and patient span of time. No designer was needed. No central authority directed the process. Gravity pulled. Space expanded. Matter responded. And the result was order, not rigid order, not a fixed arrangement, but a living, evolving structure that continues to change on timescales far longer than any human civilization will last. The web does not have a center. It does not have an edge. It fills the observable universe wherever matter exists, stretching in all directions without preference or boundary. It is, in a sense, the universe's own handwriting, the record of how matter and energy have moved and gathered and spread across 13 billion years of history. Now that we have moved through dark matter, dark energy, and black holes separately, it is worth pausing to see how they connect. Because they are not three isolated mysteries. They are threads in the same story. And that story is about the nature of the universe itself, what it is made of, how it got to be the way it is, and where it is going. Dark matter built the structures. It provided the gravitational scaffolding into which galaxies and clusters assembled. Without it, the universe would have remained a thin, uniform fog, never condensing into the rich complexity we observe. It is the architect of cosmic structure, working quietly in the background, invisible but indispensable. Dark energy is reshaping those structures. It is stretching the universe apart, accelerating the expansion of space, and gradually increasing the distances between galaxies. Over the very long term, dark energy will win its competition with gravity. Galaxies will recede from one another faster and faster until the light from distant galaxies can no longer reach us. The observable universe will shrink, not because the universe itself is getting smaller, but because expansion is outpacing the speed of light. This is a slow process. It will take trillions of years to become dramatic, but it is already underway. Black holes are the most concentrated expressions of gravity within this story. They sit at the centers of galaxies, anchoring the visible matter around them. They form when stars exhaust their fuel and collapse under their own weight. They merge and grow over billions of years, shaping the galaxies they inhabit. And through gravitational waves, they broadcast their existence across the universe in a language that LIGO has only recently learned to read. All three phenomena, dark matter, dark energy, and black holes, share a common feature. They are detected not by seeing them directly, but by observing their effects on things that can be seen. Rotation curves reveal dark matter. Distant supernovae reveal dark energy. Gravitational lensing and stellar orbits reveal black holes. The universe has a habit of showing us its influence before it shows us its substance. This is not a failure of observation. It is a feature of how gravity works. Gravity is the weakest of the fundamental forces, but it is also the most universal. It acts on everything, across all distances, and it shapes the largest structures in the cosmos. And because it cannot be blocked or shielded, it always leaves a trace. Even when the thing producing it refuses to reveal itself in any other way, gravity still speaks, and astronomers have become very good at listening. The cosmic web, the vast network of filaments, clusters, and voids that fills the observable universe, is the visible result of all three forces working together across billions of years. Dark matter formed the initial framework. In the early universe, it collapsed first, assembling into halos that would become the gravitational anchors for everything that followed. Those halos attracted ordinary matter, which settled into them and began forming stars, planets, and eventually galaxies. The filaments of the cosmic web trace the paths along which dark matter flowed in the early universe, drawing ordinary matter with it. Black holes formed within those galaxies, at their centers and scattered throughout. They grew by consuming gas and dust and, occasionally, stars. The supermassive black holes at galactic centers influenced how galaxies evolved, regulating the rate of star formation and shaping the properties of the gas surrounding them. When galaxies merged, a common event across cosmic time, their black holes merged too, sending gravitational waves rippling through space-time. Dark energy, meanwhile, was quietly reshaping the distances between all of these structures. The expansion it drives is not visible on the scale of individual galaxies or clusters. Gravity holds those together firmly enough to resist the expansion locally. But on the largest scales, between clusters and across the voids, dark energy's influence is unmistakable. It is the reason the universe is larger today than it was yesterday. And it will continue to be the reason the universe is larger tomorrow. What emerges from this picture is not chaos. It is not randomness or disorder or a universe falling apart. It is a story of forces in balance, of structures forming and evolving across immense timescales, of matter and energy flowing through the cosmos in patterns that are, when viewed from far enough away, remarkably coherent. The universe is not simpler than we thought. It is richer, more layered, more subtle, and in that richness there is not less stability, but more. The same physical laws that govern a falling apple govern the motion of galaxy clusters across billions of light years. The same gravity that holds you to the ground built the cosmic web. The same space-time that lets you walk from one room to another stretches and curves around black holes at the centers of galaxies. Everything is connected by the same quiet, patient forces. and those forces have been at work for 13.8 billion years, producing a universe that is, by any measure, astonishing. There is a temptation when confronted with numbers like 95% to feel small, to feel that the universe has been hiding something, that the story we thought we knew was incomplete, that the ground beneath our understanding has shifted. But consider what has actually happened. Humans looked up at the sky and wondered what was there. They built instruments to look more closely. They developed mathematics to describe what they found. They tested predictions against observations, refined theories, and gradually assembled a picture of the cosmos that spans from the smallest subatomic particles to the largest structures in the observable universe. Along the way, they discovered that the universe was larger than anyone imagined, older than anyone guessed, and made of things that no one had ever suspected. Dark matter, dark energy, black holes, gravitational waves, the cosmic microwave background. Each discovery did not diminish understanding. It expanded it. The fact that 95% of the universe is invisible does not make it less knowable. It makes it more interesting. It means that the universe still has things to teach us. That the story is not finished. That the questions we are asking now will lead to answers that will themselves raise new questions. And that this process, slow, careful, patient, will continue for as long as there are minds curious enough to ask. And there is something else worth sitting with. The invisible parts of the universe are not hostile to us. They are not threatening our existence or destabilizing the world we live in. Dark matter holds galaxies together. It helped build the structures that allowed stars and planets to form in the first place. Without it, there would be no Earth, no sun, no life of any kind. Dark energy is reshaping the universe on scales so vast and timescales so long that it has no effect on anything happening here, now, today. The expansion it drives is imperceptible at the level of solar systems, of galaxies even. It operates on the largest scales, the longest timescales, in a way that is quiet and unhurried. Black holes, for all their dramatic reputation, are calm gravitational anchors. They sit at galactic centers and do their work quietly, shaping the slow rotation of galaxies without demanding attention. The one at the center of the Milky Way has been there for billions of years, and here we are, unaffected, orbiting at a safe distance, living our small and quiet lives within a galaxy that a black hole helped to organize. The invisible universe is not a threat. It is a foundation. Science does not end with a discovery. It deepens with one. The identification of dark matter, dark energy, and black holes as major components of the universe opened doors to questions that are still being explored today. Each answer produced new puzzles, and each puzzle attracted new instruments, new methods, and new generations of scientists. This is how understanding grows, not in a straight line toward a final truth, but in expanding circles, each one wider than the last. For dark matter, the central question remains: what is it made of? The search for dark matter particles has become one of the largest and most sustained efforts in modern physics. Underground laboratories on several continents house detectors of increasing sensitivity. The LZ experiment in South Dakota, mentioned earlier, represents the current state of the art for WIMP detection. Its detector is filled with liquid xenon, a substance chosen because it produces a faint but measurable flash of light when a particle collides with one of its atoms. If a WIMP were to collide with a xenon nucleus, the detector would register the event. So far, no WIMP has been detected. This does not mean WIMPs do not exist. It means either that WIMPs are rarer than some models predicted, or that they interact even more weakly than expected, or that dark matter is made of something else entirely. Each possibility leads to a different set of experiments and a different set of predictions. The axion search, meanwhile, has gained significant momentum. Axions were originally proposed to solve a problem in quantum chromodynamics, the theory that describes how quarks and gluons, the constituents of protons and neutrons, behave. But they also fit neatly into the dark matter picture. If axions exist, they would be extraordinarily lightweight and extraordinarily abundant, far more numerous than WIMPs would be. Detecting them requires converting them into photons using powerful magnetic fields, and several experiments around the world are refining this technique. There is also a possibility that dark matter is not made of a single type of particle at all. Some theorists have proposed that dark matter could be a mixture of different particles, or that it could have its own internal interactions, dark matter particles interacting not only with gravity, but with each other, through forces that have nothing to do with ordinary matter. This idea, sometimes called self-interacting dark matter, is being tested through observations of galaxy cluster collisions, like the Bullet cluster. If dark matter particles interact with each other, the dark matter in colliding clusters should behave slightly differently than if they do not. Observations are still accumulating, and the picture is still becoming clear. Another avenue of inquiry comes from the James Webb Space Telescope. Launched in December 2021, Webb has been observing the early universe with unprecedented depth and clarity. Its infrared detectors allow it to see galaxies that formed when the universe was less than 1 billion years old. Some of these early galaxies have turned out to be surprisingly massive and bright, more so than many models predicted. Understanding why requires a deeper understanding of how dark matter halos formed and grew in the earliest epochs of cosmic history. Webb's observations are actively refining our picture of dark matter's role in the universe's earliest chapters. For dark energy, the questions are equally deep. The most fundamental is whether dark energy is truly constant, the same everywhere, at all times, or whether it changes over the history of the universe. If dark energy is constant, it is described by Einstein's cosmological constant, a single number built into the equations of spacetime. If it changes, it is something more complex, a field, perhaps, that evolves as the universe expands. The distinction matters enormously for understanding the long-term fate of the cosmos. Current observations, including those from the Planck satellite and from ground-based surveys of distant supernovae, suggest that dark energy has been remarkably stable over the history of the universe. But the measurements are not yet precise enough to rule out slow, subtle changes. This is why several major observational campaigns are underway. The Euclid spacecraft, launched by the European Space Agency in 2023, is designed to map the large-scale structure of the universe with extraordinary precision. By measuring the positions and redshifts of millions of galaxies, it will trace how the expansion rate of the universe has changed over time. If dark energy is varying, Euclid should be among the first instruments to detect it. The Vera Rubin Observatory, currently being completed in Chile, will survey the sky with unprecedented speed and depth. It will observe billions of galaxies and detect thousands of supernovae, providing another independent measure of the expansion history of the universe. Together, these missions represent a coordinated global effort to understand the force that is reshaping the cosmos. For black holes, the questions have shifted from whether they exist to what happens inside them. General relativity predicts a singularity at the center, a point of infinite density, where the equations break down. But most physicists believe this singularity is not a real feature of nature. It is more likely a sign that general relativity needs to be extended or replaced at the most extreme conditions. A theory of quantum gravity, one that combines the principles of quantum mechanics with those of general relativity, would be needed to describe what actually happens inside a black hole. This is one of the deepest unsolved problems in physics. Several approaches have been proposed. Loop quantum gravity attempts to quantize space-time itself, treating it as composed of tiny discrete loops rather than a continuous fabric. String theory proposes that the fundamental constituents of nature are not points, but vibrating strings, whose vibrations produce the different particles and forces we observe. Each approach has its own elegance and its own challenges. Neither has yet produced a definitive prediction that can be tested against observation. But the search continues, and it is one of the most active areas of theoretical physics in the world. Universities, research institutes, and observatories on every continent are contributing to the effort. The tools are becoming sharper, the observations are becoming more precise, and the questions themselves are becoming clearer. There is also a puzzle that connects black holes to quantum mechanics in a particularly striking way. It is called the black hole information paradox. Quantum mechanics holds that information is never truly destroyed. If you know the complete state of a system at one moment, you can, in principle, reconstruct what happened before and predict what will happen next. Information is conserved. It is a fundamental principle of the theory. But if a black hole swallows information and then, through Hawking radiation, eventually evaporates completely, what happens to that information? Does it disappear? If so, quantum mechanics is violated. Does it somehow escape through Hawking radiation, encoded in the particles that leak out? If so, how? The event horizon is supposed to be impenetrable from the inside. This paradox has been debated for decades. In recent years, progress has been made using ideas from a branch of theoretical physics called the ADS CFT correspondence, which suggests that gravity and spacetime may be emergent from deeper information theoretic structures. If that idea is correct, information might not be destroyed by black holes at all. It might be encoded in a way that is not yet fully understood, but that is consistent with both quantum mechanics and general relativity. The resolution, if it comes, will likely reshape how physicists understand the relationship between spacetime, information, and the fundamental nature of reality. It is one of those questions that sits at the intersection of everything: quantum mechanics, gravity, black holes, the origin of the universe, and that will, when answered, change the story in ways that are difficult to predict from here. There is something deeply satisfying about standing at this place in the story. Not at the end, but at a place where the questions have become clear enough to pursue, where the tools are sensitive enough to test, and where the universe is beginning to answer in ways that can be heard. Dark matter, dark energy, and black holes are not permanent mysteries. They are active frontiers, places where science is working, quietly and carefully, to understand what the universe is made of and how it behaves. The answers will come not all at once, not with a single dramatic revelation, but gradually, through the accumulation of observations, the refinement of theories, and the patient comparison of prediction with evidence. That is how science has always worked, and it has never failed to eventually deliver. It is worth pausing here, in the space between the questions and the quiet, to think about scale. Not the numbers themselves, though the numbers are staggering. Billions of light years, millions of solar masses, 13 billion years. These numbers resist comprehension in the way that very large things always do. The mind acknowledges them without truly holding them. They pass through understanding like light through glass, leaving the shape intact but the weight unfelt. What is more useful than the numbers is the feeling they produce when allowed to settle. The feeling that the universe is not rushing, that it has no deadline, that the processes shaping it unfold across spans of time so vast that urgency has no meaning within them. Stars burn for billions of years. Galaxies evolve over tens of billions. Dark energy reshapes the cosmos across trillions. Nothing in the universe is in a hurry. There is a particular kind of calm that comes from understanding this. Not the calm of nothing happening, but the calm of everything happening very, very slowly. The calm of processes that are too large and too gradual to feel urgent, no matter how profound their eventual effects might be. Dark matter assembled the first halos over hundreds of millions of years. Not in an instant, not in a flash, particle by particle, gravitationally, patiently, drawing matter toward regions that were only infinitesimally denser than their neighbors. The patience required for that process is almost difficult to contemplate, and yet it happened. It happened without effort or intention. It happened because gravity is consistent, and time is long, and the universe does not need to be told what to do. The same patience applies to black holes. They grow slowly, consuming matter over millions and billions of years. The supermassive black hole at the center of the Milky Way did not appear overnight. It assembled itself across cosmic timescales, fed by gas and dust and the occasional star, growing from something much smaller into something 4 million times the mass of the Sun. That growth is ongoing. It is happening now in the quietest possible way, imperceptible from any human vantage point. And dark energy? It has been stretching space since long before any star was born. Its effect on any individual galaxy or cluster or region of space is too small to notice on human timescales. It is only across the largest distances and the longest durations that its influence becomes clear. It is the most patient force in the universe, the one that reshapes everything by doing almost nothing at all, at any given moment. Understanding this can shift how the mind holds the night sky. When you look up and see stars, you are seeing light that left those stars years ago, decades ago, centuries ago, millennia ago. The light from the nearest stars beyond our sun has traveled for years to reach your eyes. The light from distant galaxies has traveled for billions of years. What you see is not the universe as it is now, but as it was, at different moments in a long and continuous story. And beneath that story, invisible but essential, dark matter is holding the structure together. The galaxies you see are sitting inside halos of dark matter that extend far beyond their visible edges. The light is the surface. The dark matter is the depth. There is a quietness to this that suits the hour. The universe is not loud. It does not demand attention. It does not reach out and grab. It simply exists, vast and ancient and patient, carrying on its slow business of forming and dissolving and reforming structures across scales that human minds can only approximate. And somewhere within that vastness, on a small planet orbiting an ordinary star, in a galaxy held together by invisible matter, a mind is settling into sleep. The questions of the day have been set aside. The wondering has found its resting place. And the universe, indifferent to whether anyone is watching, continues its quiet work. The Planck satellite, launched by the European Space Agency in 2009, spent 4 years mapping the entire sky with extraordinary precision. Its target was the cosmic microwave background, the faint afterglow of the early universe, released when the cosmos was about 380,000 years old. This radiation fills all of space, arriving from every direction, remarkably uniform, but carrying tiny variations in temperature differences of about 1 part in 100,000. Those tiny variations are a map. They record the density differences that existed in the early universe, the same differences that dark matter would later amplify into galaxies and clusters and the cosmic web. By measuring those variations with extraordinary care, the Planck team was able to determine the composition of the universe with remarkable precision. The results confirmed what other observations had been suggesting for years. Ordinary matter accounts for about 4.9% of the universe's total energy content. Dark matter accounts for about 26.8%. Dark energy accounts for about 68.3%. These numbers are not guesses. They are measurements derived from the most detailed map of the early universe ever created. Planck also confirmed that the universe is extraordinarily flat, meaning that its geometry is very close to Euclidean, the geometry we learn in school. This flatness is itself a puzzle, because the physics of the early universe would seem to require a very specific set of initial conditions to produce it. Understanding why the universe is so flat is one of the ongoing questions that connects cosmology to the deepest theories of physics. The data from Planck continues to be studied and refined. Scientists are still extracting new insights from its measurements, years after the mission ended. It is one of those data sets that will be used for decades to come, providing a window into the universe's earliest moments that no other instrument has matched. Consider, for a moment, what it means to live inside a universe where most of what exists is invisible. Not hidden, exactly. Not concealed behind something or locked away in a place we cannot reach. Simply present in a form that does not announce itself through light. Dark matter surrounds every galaxy, every star, every planet, including ours. It passes through us constantly, billions of dark matter particles, if WIMPs are what they might be, flowing through your body every second, interacting with nothing, leaving no trace. This is not unsettling. It is, in a quiet way, ordinary. Most of what happens in the universe happens without being seen. Stars form inside clouds of gas so thick that visible light cannot penetrate them. Galaxies merge over timescales so long that no single observer could witness the process. The expansion of space occurs everywhere simultaneously and affects nothing at the scale of daily life. The universe conducts most of its business quietly, and it has been doing so for 13 billion years without any difficulty at all. There is a parallel here to how we experience the world around us. Much of what sustains us is invisible. The air we breathe, the magnetic field that shields us from harmful radiation, the gravitational pull that keeps us on the ground, the water cycling through soil and atmosphere, replenishing rivers and lakes and clouds. None of these things demand our attention. They simply work. They have been working long before any human noticed them, and they will continue working long after. Dark matter is like that, but on a cosmic scale. It is the quiet infrastructure of the universe, the invisible support system that makes everything else possible. And it does its job without ever being thanked, without ever being seen, without ever needing to be. Dark energy, too, operates on a scale that removes it from immediate concern. Yes, it is accelerating the expansion of the universe. Yes, it will eventually carry distant galaxies beyond our ability to observe them. But that process is unfolding over timescales measured in trillions of years. On the scale of a human life, or a civilization, or even the life of a species, dark energy is as quiet and unthreatening as a gentle breeze in a vast open field. It is there. It is real. But it asks nothing of us. And black holes, as we have seen, are not the devouring monsters of popular imagination. They are gravitational anchors. Patient, ancient, quietly shaping the galaxies they inhabit without disturbing the life that flourishes within them. Sagittarius A times has been at the center of the Milky Way for billions of years. It has changed nothing about our daily existence. It has simply been there, doing what gravity does, holding things in place. What the invisible universe teaches us, perhaps, is something about the relationship between understanding and trust. We do not need to fully understand something in order to rely on it. We trust that the ground will hold us up, even though most of us have never studied geology. We trust that the sun will rise tomorrow, even though the nuclear processes that power it are beyond everyday comprehension. We trust that the air will continue to sustain us without ever thinking about atmospheric chemistry. The universe extends this same principle to its largest scales. Dark matter holds galaxies together, and we do not need to know exactly what it is made of in order to benefit from that gravitational stability. Dark energy is reshaping the cosmos, and we do not need to understand its nature in order to live peacefully within it. Black holes anchor galactic structure, and we do not need to solve the information paradox in order to orbit safely within a galaxy they helped to build. Trust does not require complete understanding. It requires only that the systems we depend on continue to function. And they do. They have for billions of years. They will for billions more. There is also something worth reflecting on about the nature of invisibility itself. We tend to think of the visible world as the real world. What we can see, touch, measure directly, that is what exists. Everything else is speculation or theory or abstraction. But the universe has gently corrected this assumption over and over throughout the history of science. Radio waves are invisible. They were invisible for centuries before anyone suspected they existed. When James Clerk Maxwell predicted them mathematically in the 1860s, there was no way to detect them. It took decades before Guglielmo Marconi and others built instruments sensitive enough to capture them. Now we use them to communicate across the globe. Infrared light is invisible to the human eye. It was discovered in 1800 by William Herschel, who noticed that a thermometer placed beyond the red end of a visible spectrum registered a rise in temperature. Something was there that could not be seen, but could be felt. Bacteria were invisible for most of human history. They caused disease, fermented bread, and shaped ecosystems, all without anyone knowing they existed. When Antony van Leeuwenhoek first observed them through a microscope in the 1670s, an entire world opened up. Dark matter and dark energy follow the same pattern. They were invisible. They were unsuspected. And then observations accumulated, instruments sharpened, and scientists began to see indirectly, through effects and signatures and gravitational fingerprints, that something vast and important had been present all along. Invisibility does not mean absence. It simply means that the tools for detection have not yet caught up. And in the case of dark matter, they may never catch up in the way we are accustomed to. We may never hold a dark matter particle in a lab the way we hold an electron in a beam, but we can still understand it. We can still map its distribution across the universe. We can still predict its behavior with precision. And that is a form of knowledge that is, in many ways, more impressive than simply seeing something. It is the knowledge that comes from listening to the universe's deeper rhythms, from following gravity where it leads, from trusting mathematics when it points towards something that cannot yet be seen. The universe began, as far as current understanding reaches, about 13.8 billion years ago. In the earliest moments, it was extraordinarily hot, extraordinarily dense, and extraordinarily small. Matter and energy were packed together in a state so extreme that the physics governing it is still being worked out. From that beginning, the universe expanded and cooled. Matter began to form. Light became free to travel for the first time, filling space with the faint glow that the Planck satellite later mapped in exquisite detail. Dark matter halos assembled. Ordinary matter fell into them. Stars ignited. Galaxies formed. Clusters gathered. The cosmic web took shape. Along the way, dark energy was doing its quiet work, stretching space, widening the gaps between structures, reshaping the geometry of the universe on the largest scales. Black holes formed within galaxies grew by consuming matter and sent gravitational waves rippling outward each time they merged. All of this happened according to the same physical laws that operate today. The same gravity, the same electromagnetism, the same quantum mechanics. The universe did not change its rules along the way. It simply had more time to work with. And the result is what we see when we look up. A sky full of stars, each one burning with nuclear fire, each one orbiting within a galaxy that dark matter built, each one drifting gently outward as dark energy stretches the space between them. A universe that is vast and ancient and still evolving, but also stable, consistent, and deeply, quietly trustworthy. There is a long tradition in human thought of looking up at the night sky and feeling two things at once: wonder at the scale of what is out there, and comfort in the fact that it is still there, night after night, following patterns that can be predicted and understood. That tradition does not end with the discovery of dark matter and dark energy. It deepens. Because now, when you look up, you are not just seeing the stars. You are seeing the visible edge of something much larger. A universe that extends far beyond what light can show us, made of substances that have never been directly observed, shaped by forces that operate on scales so vast that human lifetimes are too short to witness them. And yet all of it is there, is less than #0. 5 hash is greater than. All of it is real. All of it is being studied carefully and patiently by people who spend their careers listening to the universe's quietest signals. The night sky is not less full than it appears. It is more full. The darkness between the stars is not empty. It is alive with invisible structure, invisible motion, invisible forces that have been shaping the cosmos since the very beginning. And that darkness is not something to fear. It is something to sit with, quietly, patiently, with the same trust that the ground beneath you will hold, and the sun will rise, and the air will continue to sustain you long after you have stopped thinking about any of it. The universe does not need us to understand it in order to function. It has been functioning beautifully, quietly, and consistently for 13.8 billion years. Dark matter has been holding galaxies together for most of that time. Dark energy has been reshaping the cosmos for longer than any human civilization has existed. Black holes have been anchoring galactic structure since the first galaxies formed. None of these things waited for us to notice them. They simply were. And they will continue to be. What we have done, what science has done, is not discover these phenomena for the first time. It is begin to understand them. Begin to see the shape of the invisible. Begin to hear the quiet signals that the universe has been sending all along. That understanding is still young. It will grow. It will deepen. And as it does, the story will not become less reassuring. It will become more so. Because every layer of understanding reveals a universe that is more ordered, more consistent, and more gently reliable than the one before it. The question we began with tonight was a simple one, or it seemed simple. What is the universe made of? The answer, as it turns out, is stranger and more beautiful than anyone expected. Most of it is invisible. Most of it has never been directly seen. And most of it does not interact with us in any way we can feel. And yet it built everything we have ever known. Dark matter gathered the first structures. Black holes anchored the galaxies that followed. Dark energy stretched the space between them, slowly and gently, giving the universe room to grow. And ordinary matter, the 5%, the thin, bright layer that includes every star and every planet and every living thing filled in the details, burned with light, formed worlds, gave rise to minds that could look back at the universe and begin to wonder what it was made of. There is a quiet circle in that. The universe produced the conditions for its own examination. It built the structures that would eventually shelter the minds that would ask the questions that would lead back to the structures themselves. Dark matter made galaxies possible. Galaxies made stars possible. Stars made planets possible. Planets made life possible. And life, in time, made curiosity possible. The invisible and the visible are not separate stories. They are the same story, told from different angles. And we, sitting here in the thin, bright layer, are part of both. Tonight, you have travelled through some of the deepest questions the universe has to offer. Not to solve them entirely, they are still being explored, still being refined, still yielding new surprises. But to understand their shape, to see where they come from, to feel, perhaps, that the unknown is not a place to avoid, but a place to rest beside. The universe is patient. It does not demand that you understand it before it lets you sleep. It has been running quietly, reliably, and beautifully for longer than words can comfortably hold. And it will continue to do so long after this thought has faded, long after the questions have been set aside for the night, long after sleep has come and gone, and the morning has arrived with its own quiet certainties. The stars will still be there. The dark matter will still hold them in place. The black hole at the center of the Milky Way will still be anchoring the slow turn of the galaxy. Dark energy will still be stretching the space between clusters, gently and without hurry. Everything will continue, as it always has, as it always will. The universe does not need your attention to keep going. It only needs time, and time, as we have seen, is something it has in extraordinary abundance. Better sleep, a lighter day.